Property 5 concerns moments. Here is the result. If t is an exponential random variable with failure rate lambda, then the expected value of t raised to the s power is gamma of s plus 1 divided by lambda to the s for s values greater than -1. The gamma function is defined right here, and we'll look into it in more detail in subsequent slides. This definition is good for s values greater than -1, but if you assume that s is a non-negative integer, this particular result collapses to this. The expected value of t to the s is s factorial divided by lambda to the s. If you then set s equals 1, 2, 3, and 4, and do a little bit of algebra, you can find that the expected value of t is 1 over lambda for an exponential random variable. The variance is 1 over lambda squared. The coefficient of variation is 1. The skewness is 2. And the kurtosis is 9. Here is a proof of the result. The expected value of t to the s is the integral from 0 to infinity of t to the s lambda e to the minus lambda t dt. This right here is the probability density function of an exponential lambda random variable. This integral is over the support of an exponential random variable, so the rationale behind this first step is nothing more than the definition of the expected value, and in this case, taking the expected value of t raised to the s power. If you take this integral and perform the substitution x equals lambda t, and of course dx is going to be lambda dt, when you make that substitution, the integral will now look like this. Finally, the last step here, if you replace the integral with gamma of s plus 1, so this time we're relying on the definition of the gamma function, you prove the result. So here is a quick review of the gamma function. As seen earlier, the gamma function is defined as the integral from 0 to infinity of y to the alpha minus 1 e to the minus y dy, and that is for any alpha greater than 0. It is more general, however, and the gamma function is defined for negative values except on the integers, but we'll stick with pretty much positive values in what we need here for reliability. Here are some notes on the gamma function. First of all, when alpha is an integer, gamma of alpha becomes alpha minus 1 factorial. So it turns out the gamma function is a smoothing of the factorial function. We'll see a picture of that on the next page. Second result, gamma of alpha plus 1 is alpha times gamma of alpha for alpha greater than 0. Third, gamma of 1/2 is the square root of pi. And then there's three more kind of more exotic results associated with the gamma function. First is Euler's reflection theorem, and you can see the sine function gets involved with that. Then there is Gauss's multiplication theorem, and that is this long expression here. And if you are looking for series expansions of the gamma function, you can find them in Johnson, Kotz, and Balakrishnan, and also in Jerry Lawless's book. Here is a picture of the gamma function. We have alpha on the horizontal axis and gamma of alpha on the vertical axis. And if you remember from earlier, this is a smoothing of the factorials. So when you put in alpha equals 1, you will get 0 factorial, which is 1. When you put in 2, you will get 1 factorial, which is again 1. When you put in 3 as an argument into the gamma function, you will get 2 factorial, which is 2. And finally, when you put in 4, you will get 3 factorial, which is 6, and that is this height right here. So you can see that the gamma function here is smoothing the factorials, and if we want to throw in one more value, if you put a 1/2 in here, you get this height right here, which is the square root of pi. In reliability work, there is another function which is known as the incomplete gamma function, and it is usually defined in this fashion. Now notice this time there are 2 arguments, and the 2 arguments are alpha and x, and it is 1 over gamma of alpha times the integral from 0 to x of y to the alpha minus 1 e to the minus y dy. So the integrand remains the same, and there's only 2 differences. First of all, instead of integrating from 0 to infinity, we integrate from 0 to x. And then second, there is a normalizing constant out front, which is 1 over gamma of alpha. So the incomplete gamma function is a generalization of the gamma function. Upper limit is x rather than infinity, and it also has the scaling constant 1 over gamma of alpha. If you take the limit as x goes to infinity, this incomplete gamma function will approach 1. Here's why. If you were to put an infinity right here, you would have the gamma function. And now we have 1 over the gamma of alpha multiplied by gamma of alpha. That is clearly going to approach 1. The incomplete gamma function turns out to be the cumulative distribution function for the gamma distribution with a scale parameter of 1 and a shape parameter of alpha. There are some numerical routines that will calculate these things, and in the R language, you can use the gamma function to get the gamma function, and you can use the p gamma function to get the incomplete gamma function. In Maple, there is just one such function, and it's gamma. It just depends on how you work the arguments, whether you're going to get the gamma function or the incomplete gamma function. Here are some pictures of the incomplete gamma function. So what you notice here is you'll notice that when alpha is equal to 1/2, you get a fairly steep beginning. Comes out like this. Alpha equals 1, that turns out to be the exponential distribution there. And for alpha equals 2, now you have that CDF that looks like that. So even though I'm calling this a CDF, this is really the incomplete gamma function, and these happen to be the CDFs for the gamma distribution. Notice that they always lie between 0 and 1.